Yeah, so I'm Nathan Leigh. I'm recently associate professor at the Universidad de Concepción in Chile and a research affiliate for the American Museum of Natural History. I'd like to thank you all for having me here today. It's a very exciting opportunity, and I'm really looking forward to presenting our work. Today, I'll be talking about constructing a factory for predicting merger rates of black hole pairs. And before beginning, I'd like to highlight the significant contributions of my collaborators, Nick Stone, who's at Hebrew University, and his great skills with diffusion-based problems and solving PDEs, and Jeremy Webb, who's at the University of Toronto, and his significant expertise with running numerical simulations of star cluster evolution. And so let's start at the beginning, like all good stories do, with a few simple definitions. So what is a star cluster? A star cluster is shown here in the upper left inset. And these are gravitationally bound collections of stars. They can be home from anywhere from a few hundred to several million stars. Massive star clusters, like the one showed here are as old as the galaxy itself, about 10 billion years old. And the densest clusters can reach central densities as high as 10 to the 6 stars per cubic parsec, which, to put in that perspective, is about 1 million times higher than in the solar neighborhood. And at such high densities, the rate of collisions is also very high. And so the individual point sources of light that you see here do collide with each other directly, usually of order once every million years or so. So let's consider zooming in on the cluster and being able to resolve each point source of light that we see. What you would find is shown in the lower right inset here. And so the takeaway message from this is that most point sources of light are isolated single stars, not directly gravitationally bound to another star, but just to the potential of the host cluster. But we also see a number of unresolved binary star pairs. And so these are gravitationally bound to each other directly, while also being bound to the cluster. And we call these binary star systems. And so what is a binary star system? As I said, they're gravitationally bound pairs of objects, and they can be defined according to many parameters, typically called the orbital parameters. And one example is the component masses of the binary. So in this particular case, we're actually showing the sun with an Earth-like analog, a planet in orbit about the sun. And so we can look at the component masses. So for the sun, the component mass is 1 solar mass, whereas for the planet, it's about 5 orders of magnitude smaller in mass. We can also look at the semi-major axis, which tells us roughly how far apart the orbiting bodies are. The eccentricity tells you how elliptic the orbit is. More elliptic orbits have higher eccentricities. And the binary phase tells you where in the orbits the objects are and ranges from 0 to 360 degrees. So the planet can go around its orbit once, and when it returns, it's done a full 360 degrees. But the takeaway message here is that binary stars have several parameters used to define their orbital properties. And these orbital parameters decide, for example, merger times for black hole binaries due to gravitational wave emission. But when and how might these orbital properties change? Well, as I mentioned, in dense environments, it often occurs that single stars collide directly with binaries, and this will change their orbital properties. But in general, why do we care about binaries in dense star clusters? Well, one of the primary interests today is for making black hole binaries that later merge and are detected via their gravitational wave emission. This is called the dynamical channel for making black hole binaries. And how does it work? Well, let's consider zooming in on the core of a dense star cluster, such as the one shown here, 47 Tuc. We'll find a particular black hole, and we'll follow it as it orbits throughout the cluster. It's only a matter of time before it encounters a binary star system, and a gravitationally bound chaotic interaction ensues. And the way these interactions tend to unfold is they tend to continually break apart into these hierarchies with a temporary single going on a prolonged excursion, as shown here, leaving behind a temporary binary star system or a temporarily close gravitationally bound pair. This breaking apart into hierarchies continues. Sometimes the excursions are short-lived, sometimes they're long-lived. But if all particles are point particles, such that no collisions are possible, then the interactions inevitably end with the ejection of one particle to spatial infinity, leaving the other two particles bound in a binary. And importantly, it's usually the least massive object that is ejected from these interactions. And in star clusters, its black holes tend to be the most massive object. So there goes the least massive object in the interaction, and the interaction is now over. So black holes tend to be the most massive objects in star clusters. So when these black holes encounter binaries, we often get what are called single binary exchange interactions, where we are systematically exchanging black holes into binaries. And we can now imagine we have this black hole star binary pair traveling throughout the cluster. Another black hole comes in, another chaotic three-body interaction ensues, ending with an exchange. And we would be left with two black holes in a binary star system that could later merge and be detected via their gravitational wave emission. And so this is the dynamical channel for making black hole binaries. Okay, but what we want to know how do single binary scatterings, if, for example, what you just saw was a scattering, so having each pair of particles, each pair of objects coming in from spatial infinity, we call this a scattering experiment. So how do single binary scatterings, as occur in dense star clusters, modify the distributions of binary properties over time? And do they make a big difference to black hole merger rates? Well, to calculate this, what we can do is derive a Boltzmann or diffusion equation to evolve a population of binary star systems forward through time due to single binary scatterings in dense stellar environments. And so we'll consider a population of binaries all orbiting within a star cluster. And this is analogous to a population of binaries in a thermal bath, with heat being transferred from the binary stars to the singles via single binary interactions, providing a heat source in the process. And so given initial distributions of binary orbital parameters and the host cluster properties, the diffusion equation can evolve the binary population forward through time due to dynamical interactions between single and binary stars. And I've written here just a very simple version of a first order diffusion equation to convey the general concept. Basically, we balance the rates at which binaries populate the different bins in orbital energy in this case. Binaries flow into each bin and out of each bin due to single binary scatterings. And the key point, or the key thing to highlight, is this function right here. Since this is the critical ingredient, since it provides the outcome distributions for three-body scatterings. So the first step in this project was Stone and Leigh 2019, where we derived the required outcome distributions for chaotic regions of phase space, such that we no longer need to perform simulations of three-body interactions. Thanks to this function, we now have an analytic function describing the outcome probabilities to work with, and can build a completely analytic diffusion-based model with these probabilistic functions. And so in doing this and building this diffusion-based model, what we gain is a technique that is independent of computational methods to understand the dominant physics evolving binary populations in dense stellar systems. And this is potentially a game changer for the problem, which is very difficult to tackle with computers, since the addition of binaries makes the computations prohibitively expensive. But because the method is analytic, we can sweep through the parameter space of initial conditions with minimal computational expense. And so briefly, just to show you how well our analytic model, this probability density function that we've derived, reproduces the simulated data. So we show the distributions of final binary orbital energies on the x-axis as a function of the total initial interaction energy. And this function gives the probability of obtaining a binary in any given bin in orbital energy post-interaction. So the solid lines show our simulation results, the dashed lines show our analytic predictions, and the color coding indicates different initial binary orbital eccentricities, which changes the total interaction angular momentum. Our method reproduces the simulated data quite well, and we even improve upon all previous attempts because our method, this was the first time we were able to do this from first principles. And so we get better agreement between our simulations and our theoretical predictions than was possible before. But one really cool thing that came out of this is the final distribution of binary orbital eccentricities post-interaction. And so again, we have the probability of obtaining any given orbital eccentricity, or the probability of obtaining any given orbital, the probability of obtaining a binary in any given bin in orbital energy. And I will highlight, so first of all, the black dashed line shows the classic Hegge result, which assumes steady state balance between binary creation and destruction. And this is just a thermal eccentricity distribution. And I'll highlight the green and the yellow curves, which correspond to the very low angular momentum limit. And for these cases, we find suprathermal eccentricity distributions. So our formalism potentially predicts more eccentric black hole binaries from the dynamical formation channel than previously predicted, which could enhance the rates of black hole binary mergers due to gravitational wave emission. But the takeaway message here is that with this new probabilistic theory, simulations of the general three-body problem do not need to be performed anymore, since we know the probabilities for any given outcome. So we can now construct a purely analytic model to do the diffusion-based calculations that we're after. Of course, right. So with our probability density functions now derived, we're ready to move on to the next step, which is to evolve an entire population of binaries due to single binary scatterings. What we really want is...
Sorry, Nathan, we just have a question, if you don't mind.
Oh, sure, sure.
Sigurd, do you want to go
ahead? Yeah, sure. Can you hear me?
Yes, yes.
Yeah, so in the previous slide, I just wondered how, so there's some scatter in the numerical lines, right? The expensive ones.
Yes.
I wonder is that scatter big enough to explain the whole difference between the dashed lines and the solid lines, or can you actually measure that there is a deviation here?
Could you repeat the question? So you're asking how good our agreement is?
Yeah, exactly.
Yeah. I think yeah, it's a little hard to see here. It's been a while, so I suspect that it's just due to the number of simulations that we lost. But we've done extensive subsequent work, since there's all sorts of tests you can do to test the robustness of your model. We just perform the scattering experiments, generate our distributions, and then compare to analytic distributions that we see.
Yeah, running more sims was the thing I was going to suggest, but if it's
Yeah.
expensive, then yeah.
You also get it helps predict which of the three particles will be ejected, so we can test that. There are all sorts of additional tests done on top of this, and I agree, the data, they're clearly super thermal, but yeah, we could get into the data analysis a little more robustly. Maybe we could talk about that afterwards if you wish. Okay, so what we really want is a more sophisticated diffusion equation that goes beyond first order, but the idea remains the same. We balance the rate at which binaries populate the different bins in orbital energy. Binaries flow into each bin and out of each bin due to single binary scatterings. And we integrate into our model a Fokker-Planck formalism and couple the single binary interaction evolution to that of the host cluster. And just very quickly, as before, what we needed to compute our diffusion coefficients was this function right here, which is what we derived in Stone and Leigh. So before getting into showing some results, I'd like to briefly motivate it by discussing what the goals are and what we hope to obtain from our model. So what can we do with our analytic model? One thing we can do with our diffusion formalism is to predict the rates of black hole mergers in dense stellar environments due to the dynamical formation channel. So we get population statistics for a wide set of initial cluster conditions for comparison to observational data. And this is important since we are very clueless about the initial conditions and, for example, how many stars, black holes, neutron stars, and so on should be present in a given cluster at a given time. Because our method is analytic, we can rapidly sweep through the parameter space of initial conditions and isolate the influence of 3 and 4 body dynamics in deciding the overall merger rates coming from this channel. And currently, no model for star cluster evolution can cover the entire parameter space relevant to real star clusters. So ours is the first method that can do so, while also including physical effects that other methods are not able to capture. We can also predict the rates of formation of various types of stellar exotica, where either collisions are required or the exchange of a compact remnant into a binary system is needed. And examples include the formation of low mass X-ray binaries, where you exchange a neutron star into a binary star system. Millisecond pulsars, which are thought to be evolved low mass X-ray binaries, where the neutron star is accreted and been spun up. We can do blue straggler formation and the collisions of main sequence stars, runaway collisions, and seeding supermassive black holes. We're expanding to include binary-binary interactions in our formalism, and so on. And so by our method being able to compute simultaneously for a given set of initial conditions, population statistics for all sorts of exotic binary populations that are all measurable in star clusters, we can use all of this to break degeneracies and isolate which initial conditions actually must have been the ones to evolve to give us what we see today. And so it's very important to be doing these calculations self-consistently and complementarily, since the numbers and properties of the exotic binary system should ultimately correlate with the black hole merger rates. All right, let's look at what happens when we solve our diffusion equation and evolve the distribution of binary orbital energies forward through time due to single binary scatterings. So what we're going to do is we're going to begin with a one-zone model where we assume that everything that happens in the core stays in the core. So we have single binary interactions happening in the core, and we assume, so when a single binary interaction ends, the single star gets ejected, and the binary gets a recoil velocity decided by linear momentum conservation. And it can occur that the recoil velocity is large enough for the binary to get kicked out of the core. And this does happen in our simulations. So we'll start with this one zone model, and we'll see how good the agreement is between the n-body simulations and our predictions from our diffusion equation, and how important not having this additional sync term in actually is. But then we'll move on, we'll improve upon this and go to a two-zone model where we allow for binaries to flow in and out of the cluster core. So starting with our one-zone model, we can integrate analytically over our diffusion equation for a period of 100 relaxation times, shown at different times via the colored dashed lines. The x-axis shows the final binary energy post-interaction, normalized by the total interaction energy. The y-axis shows the fraction of binaries in each bin in orbital energy, and this is exactly equivalent to the function we derived f of EB in Stone and Leigh. The black line shows what we assume for the initial distribution of binary orbital energies, and it is called Upik's law. And this is just an analytic power law distribution motivated by observations of young binary populations thought to be unmodified by dynamics. And so there's the power law there with the power law of -1. And so I'll highlight the left end is the wide end where wide binaries reside. And the right end is the compact end where compact binaries reside. And what we find is that we start with more wide binaries than compact binaries. But over time, the evolution tends to make these binaries more compact. And the reason for this is simply because these single binary exchange interactions tend to systematically impart additional kinetic energy to the singles. So singles tend to leave with more kinetic energy they came in with. And so that's providing both a heat source to the cluster while also making the binaries more compact. We also see depletion in our binary population. And this is because we include sink terms at the boundaries. And so if a binary here becomes wider than this limit, we remove it from the population since we assume that it will be rapidly destroyed via a subsequent single binary interaction. If a binary is here and just beyond this boundary, we assume it's become so compact that it will merge due to gravitational wave emission before the next single binary interaction occurs. And we can compare these results to the results of n-body simulations of star cluster evolution. So the colored points here show the results from our n-body simulations, whereas the dashed lines show our solution from the diffusion equation. That we follow the time evolution of the binary orbital energy distribution function again on the y-axis as a function of the post-interaction binary energy, still normalized by the total interaction energy. And what we find is that the agreement between our analytic model, shown by the dashed lines, and the n-body simulation, shown by the data points, is generally quite good at the wide and compact ends, but we systematically underpredict in the simulations the number of binaries by a factor of about 2 relative to our analytic predictions. So let's see how we can improve upon this by going to a 2-zone model where we allow for binaries to flow in and out of the cluster core, and if we can improve the agreement in this region. And so just to remind you, we're now moving to the picture on the right, where we allow for binaries to flow in and out of the cluster core. And so to remind you, these 3-body interactions end with a single being ejected, and the binary gets a recoil velocity decided by linear momentum conservation. But once the binary is out of the core and it's in the halo, since we assume all equal mass particles for these simulations, the binaries tend to be heavier than the other stars in the system. So by energy equipartition, they systematically slow down, imparting additional kinetic energy to giving up kinetic energy to the other singles. And they sink deeper in the cluster potential and can drift back into the core due to mass segregation. So we need both a sink.
So Nathan, you have 5 minutes.
Okay, almost done. So we have a sink term to remove binaries and also a source term to put them back in when they migrate back in due to 2-body relaxation. And so let's look at the time evolution of our 2-zone model. So binaries in the core are shown in blue, whereas binaries outside of the core are shown in red. And we start with 50% binary fraction in both the core and the halo. And if we let this evolve, what we see is that the core population tends to evolve faster because of higher densities, both in terms of losing the initial population to the halo, and also draining into the hard soft boundary beyond which the binaries are destroyed or ionized. So the takeaway message here is that by playing around with our boundary conditions, which are decided via sink and source terms in our Boltzmann or diffusion equation, we can improve the agreement between simulations and our analytic model quite substantially. The parameter space is huge, unfortunately, and which sink and source terms are important change with the properties of the host cluster. So the next step is to understand how and when these correction factors should be implemented for the entire parameter space relevant to observed star clusters. And briefly, I can just show that the agreement is indeed improved for our two-zone model. So this plot is a little bit busy, and I'll show the core and halo populations separately in just 1 second. But just to what we're showing here is the colors show the binary distributions at time t equals 0 in black, after 12 core relaxation times in blue, and after 100 core relaxation times in green. The dashed lines and open dots show core binaries, whereas the solid lines and solid dots show halo binaries. And let's take a look at the core first. So looking at the core, we find excellent agreement between our analytic model and the results of numerical simulations. However, the error bars are large, so the agreement is typically good to within 1 standard deviation or less, but the error bars are large, and this is because at any given time, we typically have of order 20 to 50 binaries in the core, and more like 150 to 200 in the halo. So we have better population statistics out in the halo. And so if we look at the halo, this is what we see. Again, we see overall good agreement with the model and with simulated data and the model agreeing to within typically about 1 standard deviation or so. And so indeed, by adding additional sink and source terms, we are able to significantly improve the agreement between our numerical simulations and our analytic model. And just to conclude, so what can we do with our model? Well, as I said, we can predict the rates of black hole mergers in dense stellar environments due to the dynamical formation channel with minimal computational expense as a function of the initial conditions. Similarly and complementarily, we can predict production rates for other types of exotic binary populations. So we get population statistics for a wide set of initial cluster conditions for direct comparison to observational data. And by comparing subsequently to empirical data, we can then work backwards to constrain the initial conditions in dense stellar environments. But how does this work? Well, one example of this comes from the fact that our method can predict the peak density a cluster should reach during core collapse. So let's look at a particular cluster with a high central density, such as the one we began with, 47 Tuc. Well, the way this works is that as star clusters evolve, heat flows from the core to the halo, causing the core to contract. The core is a negative heat capacity system, so this contraction heats it up further, and it's ultimately a runaway process called the gravel thermal instability that ends with a singularity at the origin. And this contraction should continue indefinitely, but what stops it are single binary interactions. And this is because on average, the ejected single leaves with more kinetic energy post-interaction, providing a heat source in the core. So with our model, we can compute the exact point and the corresponding peak density at which the rate of energy flow out of the core due to two-body relaxation exactly balances the rate of energy flow into the core from binary single interactions. And so this immediately informs us about the underlying binary population, since, for example, if we see that very high central densities are reached, then this could suggest low binary fractions, since there are apparently too few binaries to supply the needed heat source, right? If you see a very, very high central density, one way you can explain that is just if there are insufficient binaries in there, then you'll have to keep going to higher and higher densities until the rate of single binary interactions increases significantly for that heat source to become sufficient to bounce the cluster out of core collapse. And that's it for me. But before concluding, very quickly, I'd like to advertise a recent textbook called Moving Planets Around. Please check it out. It's if you're interested in celestial mechanics and designing versatile software environments for use in astrophysics-based research. Our focus is on exoplanet systems and teaching undergraduate and graduate students how to get directly involved in and contribute to peer review level research in computational and theoretical astrophysics. And thank you again for having me, and I'll take questions.
Thank you very much, Nathan, for that very very interesting talk. So we have some questions. First, we'll go with Mathieu.
Hi, yeah, thanks. This was very interesting. I was wondering if you're keeping track in your formalism of the particles that are ejected, because that could give you another observational comparison point with dynamically ejected runaways, for which we are starting to have a lot of Gaia data.
Great. So for, yes, it's exactly what we can do. So the next step, so for our simulations, the central densities are not high enough for binaries to typically, they're not high enough for the energetics to be enough to kick the binaries out of the cluster. So we really don't see it happen in our simulations. But where we need to go next is to denser initial configurations, because we'll have to include a source term for binary formation, because they can, 3 single stars can meet and form a binary in very, very dense environments. And we'll also have to include sync terms for binaries and stars actually leaving the cluster.
Yeah, I think also
yeah.
the single stars ejected would be very interesting.
We'll get all of it. Absolutely, yes.
Okay, thanks.
Okay, Amiel.
Wanted to know, thank you for the interesting talk. I wanted to know whether in your formalism, especially when coming to apply to observations, you're taking stellar evolution processes into account. I assume you are not, but I'm wondering, whether, how things like mass transfer when the 2 stars are very close to each other, common envelope evolution, and just general evolution would affect the dynamics.
Absolutely. So I think you have to do that. So what we'll get, for example, is we'll get binary populations, and we'll know each component of the binary, and we'll know the properties of the binary. And so some of our binaries will not be Roche-Loeb filling, but we can immediately, we can calculate if they will become Roche-Loeb filling when they hit the RGB or the AGB. And so it's also relatively easy to include like a source term or a switch in our formalism to using stellar evolution timescales to evolve stars and change their radii. And so basically what we'd get is we'd get the properties and the objects that are in there. And then we can tell you if it's going to actually accrete. So like an LMXB, is it too wide for there to be any accretion? Because if it is, you won't see it. So we'll be able to answer right away how many of these should be actively accreting and visible in the X-rays and these types of questions.
But are you saying that the stellar evolution does not affect the dynamics?
Generally, no. I mean, it affects the dynamics by changing the properties of the objects, so making them more. So for example, when you turn a red giant or an AGB into a white dwarf, you've changed the radius, and so now its collision probability has dropped substantially. But
so I wanted to know whether you're following these effects in your calculation.
not for this initial test, but this is something that we will include in there. Generally, I think you're more interested in the pairing and then figuring out which, because most of these binary populations, what you're seeing are the longer term internal binary evolution. So what you really want to know is what kind of binaries you set up and which ones will be visible in X-rays. If you also get merger rates, so you should be able to know blue straggler numbers just by counting the number of blue stragglers that are brighter and bluer than the turnoff. And then so there, for example, with collision products, they have a period where they're inflated and will contract, give up that extra energy from the collision event on a Kelvin-Helmholtz time. And so we can certainly put that in there as well. We can include all of these effects. Just deciding which ones are the most important and which ones to focus on is I think the real question.
Thanks.
Next we'll do Catherine.
Hey, so I've got a bunch of questions, but one would be sort of how about hierarchical systems? Can you sort of treat everything as layers of binaries within binaries, and deal with hierarchical systems?
So we can indeed deal with hierarchical systems. So you don't tend to make, so where you'll make hierarchical systems is with very high binary, you'll make them in open clusters. So you actually will make them in the type of cluster that we looked at, but we weren't following, we made our, so the crossover at a binary fraction of less than 10%, single binary interactions dominate over binary interactions. So as the binary fraction goes up, you're getting more and more four-body interactions, or at least the relative rates are such that you're getting many more four-body interactions for every three-body interaction. Then you can start making triple systems, and they can be dynamically stable. And so we've done a lot of work on this, actually, trying to expand Stone and Leigh 2019 started with the four-body problem, and we have most of that done. We just need to get it published now. But yeah, no, you could tell the exact rate at which you're forming triples, you know their properties, and then you know if they're, for example, in the active Lidov-Kozai domain. But we've been able to do things like also derive the expected inclination angle distribution for dynamically formed triples between the inner and outer orbital planes. This all just needs to get published and integrated into the model.
And are the hierarchical systems important for the global dynamics, or are they just a curiosity, if you see what I'm saying?
So I think it depends on why would you want triples in there?
No, I'm asking you, right? If I wanted to know about the evolution of the globular cluster as a whole, do I only care about, can I just get away with merely all the beautiful work you've done following the binaries, or do I need to follow the higher?
So it's actually, so in a globular cluster, it's I think it's pretty hard to form triples just because the energetics are not favorable and the interactions tend to be shorter lived. But the way to think about it, I think, is if you think about star clusters like a gas cloud, a star cluster with a high velocity dispersion is a hot cluster. So interactions and collision should be dissociative and destructive, and you should have very few binaries and no triples. In an open cluster with a very low velocity dispersion, it's cold, and so the particles stick together more. And you see more higher fractions of triples and quadruples. And in fact, the interactions take longer, and you even have a high probability of an ongoing four-body interaction being interrupted by another binary before it finishes. And so then you could have a six-body interaction. And so the open cluster regime is actually the hardest because the interactions take so long that you have to worry about subsequent dynamical effects happening before the interaction's over. Whereas in very dense environments, it's just single binary interactions, since the densities are so high. they're fast. And so all of the assumptions going in, for example, to Monte Carlo simulations are actually pretty good. Like if they don't have to worry about interruption, which is something they would not capture with the Monte Carlo simulation of star cluster evolution. But so if you're interested in triples, so where it could also become interesting is if you have a central massive object there, it obviously is very important. And you would want to know, you would know what the properties of if a binary ends up bound to that central massive object, you would certainly be able to evolve it due to Lidov-Kozai or whatever, and calculate if that time scale beats interruption time scale or all these types of things. So I think it depends on the problem. Did that answer the question?
Yeah, thank you. Thank you.
So next, Barry.
Hi, Nate. That was very interesting. I'm building on Catherine's question. Is it straightforward to include a central massive object in the setup that you have in order to follow the dynamics around, say, a supermassive black hole?
Yep.
Excellent. So that's part one. Part two is, could you introduce something like a dynamic coolant, right? A sort of fake AGN disk to your sort of cluster environment and try and mimic, you know, the effect on the nuclear star cluster of having a dynamic coolant in that environment. Is that something that
you can definitely do? Like we can put a disk in. We know when stars. We could use the work that we've been doing to know, for example, how long they'll be ground down into the disk. I think adding gas in opens a lot of. I mean, it's hard, and I think we have a lot to worry about with torque prescriptions for just binaries in the disk and things like this. But absolutely, you could put in like a source of dissipation. It would just be, do I believe the source of dissipation is up? Do I believe that the way that we're doing this is actually capturing the physics correctly? I think. And so I think we'd have to talk about how to do that. But absolutely, yes, the model can do all that.
Cool. Thank you.
So I had a question for you. Yesterday, Blakesley Burkhart and I were discussing a paper that was trying to constrain the initial mass function for globular clusters and ultra compact dwarfs. And people are also talk about this a lot for early type galaxies. And one of the issues, of course, is that the present day mass function may differ from the initial mass function due to dynamical effects in those systems. Right. Is this something that you've worked on or thought about?
Can I just post it in the chat window, a paper?
Sure,
Leigh,
yeah.
Leigh and Webb 2017. Yeah, we do. We know. So basically, if you can measure the mass function in the stellar mass function in a cluster at the present day, and you can measure its in total integrated luminosity, so its total mass at the present day, then we have a formula that allows you to calculate the initial mass of the globular cluster when it first formed. We have to assume that we know what the IMF was, though. So it would be good to get into this a little more with some. Catherine's done work on this, and so I'm hoping to look at what she's done and see if we can actually, what we can do with relaxing that assumption.
Okay, yeah, because that's what I'm interested in, is saying I can measure the current mass function, and I want to back out what the initial mass function was to sort of, you know, remove the effects of any kind of dynamical effects of preferentially removing some part of the mass function.
Yeah, so I think where you end up with trouble is the heavy end of the mass function. The lighter end is generally what you can measure below the main sequence these days, right? And that's all just two-body relaxation. And the orbit through the cluster just accelerates the rate. If it's deeper in the potential, just accelerates the rate at which it happens. But if you're worried about like the upper end of the IMF, I think that's a different and challenging problem because well, I need to think about it actually. That'd be a really fun problem. Is that what you are interested in? Learn more about the high mass end of the IMF?
Personally, I am. I mean, people are very interested in the low mass end, but I mean, they're all sort of linked together, right? And I'm personally more interested in the high mass, but just kind of a general random question, just because it was in mind, yesterday exactly. So this is convenient to be able to ask it now. So
no, it would be really interesting to sit down and think about some scenarios that would break what we did, and like if we had like one massive object in there. Or even just like a binary black hole kicking things out, it changes the mass loss. There's ways to change the mass loss in this and start depleting the higher end instead of the lower end. Deplete the higher end quicker than the lower end, because everything in the core will tend to be heavy, and if you're having strong interactions, you can eject things fast. So I'd love to talk about that more, actually.
Yeah, definitely. Catherine, do you want to jump in? It seems
I do. I do. How could you tell? So picking this up with the conversation we were having, Nathan, you brought this up. Of course, you're going to guess what I'm going to say, but you should look at the tails, tidal tails. So if we look, and you said that this morning, Nathan. So if we look at the mass function in the tails, and the density of the tails is telling us something about mass loss rate. So the problem would be how far back in history you can do by going out along the tails. Hopefully you would see the mass function change, which would be really cool as you went out along the tails. Yes. So I think there's something here. I think we're forming a collaboration, Chris and Nathan. This would be really fun. I think, Chris, you're being very challenging by wanting. That's annoying. Apart from that, I think we're going in a good direction.
I missed something about me being annoying, but you broke up, so I missed it. So.
I said you were challenging because you want to know about the high mass end. I think the lower mass end obviously is going to be easier because we can see it at some level.
But we can. But I think what we can do, I think for the high mass end, you can actually really. It might be able to change the picture. I need to think about this. Yeah, the low mass end, there's stuff we can do right away. That's exciting. Exactly what Catherine was describing.